Hello everybody, in this video we will see how to model a composite precast girder bridge with an infill type of deck. This bridge is a single span integral bridge with a span of approximately 15 meters, and we'll use the TY8 type of beams for the deck. Let's have a look at the typical section on the bridge. So that's how the cross section of the bridge looks like. We have got 12 TY8 beams spaced at a distance of 765 millimeters center, and we have TYE8 or TY edge beams at the left and right edges of the bridge. We have a carriageway defined as shown here. So we have a 2 meter and 3 meter wide footways on either side of the main carriageway, and the carriageway itself will have 2 notional lanes and no remaining area. So let's see how to model this type of bridge. So here is a blank MIDAS civil file. I start with creating a node. So that's a node at the origin. Then using this node I'll create my main girders. So the length of the bridge is 15.25 meters. There you go, that's the main girder created. Now I will make similar copies in the Y direction. So you go Y, and we'll have 14 at 0.765 meters distance. That's how it looks. Okay, now we will assign some properties to our main girders. So starting with properties, material properties, add. So start with concrete C40, that's the grade of the precast girder. So I'll just type in precast girder. Then we have the concrete as a C30 concrete. If you have some other strength, you can just change it to none and change the modulus of elasticity as per the strength of concrete. So in this case we'll be using a C30 concrete for the slab and also for the abutments and piles for the integral bridge. So C30, just name it concrete, apply. Now especially for the slab we'll use a zero density concrete because we will apply the slab weight as a wet concrete load before the slab has become composite. So the same properties, everything is same. I'll just change the code to none and just type in a different name, the slab. Weight density is 0, apply, and just another one for the transverse grillage members. This will be a grillage model, so transverse elements, same property as the slab, and click OK, or sorry, apply to save it. Then a steel material for the tendons. So we'll have pretension strands, let's say 12 millimeter dia, and click OK. Then we will define some sections as well. So section, add, and PSC for the precast sections, PSC value. Now in our case the sections are going to be composite sections, infill type. So what I'm going to do is first generate the TY beams at the center and TY at the edges, and make a composite slab out of them, the composite section out of them, with the slab at the top, because an infill type of section is a very unique or general type of section. So these type of sections we will bring in from AutoCAD, but in terms of applying tendons and other properties, you can very easily not use the automatic feature of the software to generate tendons for those sections who have the slab at the top. So we'll create such sections first which have the slab at the top, and then we will bring in sections which are basically infill type, with the slab actually filled in between the gaps of the equally spaced precast girders. So first I'll generate some sections here. So that's ty8 section database, and we've got some a UK ty section, so ty8. Click OK, and say just enter some properties here. These are just design parameters, you can enter any values. So I'll just enter some values here. This has nothing to do with the analysis, and just check auto calculation for all these parameters. Display centroid, so that's how the section is generated. Apply. Then we create another one for TYE8, say left, and just go to database, TYE8, click OK, and the same procedure, 0.5, and just click auto calculation for the remaining, for the centroid. Actually these are the positions for shear stress check. So if you put in some values, say 0.2 meters and say 0.8 meters or say 0.6 meters, so these are the locations where shear stresses will be calculated. So if you specify some locations, the software will give you additional stress points. If you don't give any location here, then it will calculate the stresses at 4 stress points as shown here, and also at the centroid level. So it's up to you how many points you want for the shear stress calculation. Then the right side precast girder section, database TYE8 and -1. Click OK. Same procedure, just enter some arbitrary values and just click auto generation over here and click apply. Then we move on to making these girder sections as composite with the slab on top of it. We are not going to use this section for the modeling, but we need this for assigning tendons automatically. So to save time, we just need to create few sections which have the slab on top of them. So the slab width is equal to 0.765 meters, which is the center spacing between the two adjacent girders. So number of girders 1, and that's the effective slab width. 0.15 is the thickness of the slab on top of the girder. So for both the infill section and also for the fictitious composite section with the slab on top, the thickness of the slab just on top of the precast girder will be 150 millimeters. So we need to keep this thickness as 150 millimeters, and then we select the material for the modular ratio calculation. So for the slab, this is C30, for the girder it is C40, that's C40. Okay, now for the bridge deck, the top of the slab will be our reference for all the loads and all the live loads, and also for the tendon loads, pre-stress loads. So we have to change the offset to center top. Click OK, and make sure we have imported the correct section. So TY8, so that's our first section. So TY8, say slab on top. Show calculation results. So these are the results for before composite and after composite section. So only the girder, and this is girder plus slab. Apply, and similarly just change the name to TYE8 and say left. Import, everything is same, center top, and apply. Then we choose the TYE8, the right side section. So right side here, click OK, and then click OK to save this section. Okay, now we also have some precast edge beams. We can model them, or we can leave them, just model them as loads. So we have some precast edge beams here. Either we can model them as actual beams, or we can just model them as loads eccentrically applied to the edge beams. So what I'm going to do is just model them in this case. So I'm going to go to properties, section properties. I've already modeled them previously in a previous model, so I'm going to just import those beams. So you have an import option using which you can import sections from previous models. So I don't need these sections, I need only edge beam left and right. Click OK. There you go. So now I'm going to assign the sections to the correct elements. So let me change to the line view. So that's the line view. I'll just save this model. So example. Right, so what I'll do is this section here will be my, say, right section. Here will be my left section. Okay, I need to model another beam here. What I'll do is just shift this one, just copy this, the Y direction. Okay, right, so this is my edge beam, the right hand side. Let me see if I have assigned them correctly. Oops. So all these beams will be composite TY8 with slab on top, so it should be like this. Okay, right, so we have got 12 TY8 composite beams. Now this particular section, I'll change it to TY8 right side section, and this particular section change it to TY8 left side, and this one I'll change to edge beam left. Oops. Edge beam right, yep, and this one will change to edge beam left. Okay, now there is a slight overlap here between the girders. We can adjust them by changing the offset. So that's the right side section. So this section we can adjust the offset, make them say left top, and adjust the horizontal offset. Oops. Okay, this should be plus 0.3. So something like this. So now it's adjusted. Okay, now I will create the actual or the composite infill type of sections. I'll bring in those sections. So to bring in those sections, I've already modeled them in AutoCAD. Okay, so let me show you how I have modeled them in AutoCAD. So there's TY8 sorry, TY8 infill type of composite section. So just the TY beam, and just drew a rectangular bounding box around it. Then similarly the edge sections left and right are similarly modeled with simple line elements in AutoCAD. Now using the tools section property calculator, I will bring those sections in. So my unit system in AutoCAD was meters, so I need to make sure I have my units as meters here as well, and force units as kilonewtons. So click OK. File, import AutoCAD DXF, and just bring in those files. So that's the first one. Yes, and go to model, materials, add, and we add the materials for composite section generation. So that's girder. Elasticity for the girder is 3.5 10 to the power 7 Poisson ratio, and density of concrete. Apply, and similarly we enter the details for the slab. That's the infill slab. So let's type in infill here. And click OK. Now I'll define the number of parts for this composite section. So we have two parts here. One is the girder and the other is the infill slab. So 2 parts, and the name, we can give some name here. So composite. Base material will be the girder for section calculation, section stiffness calculation. Apply, and a new composite section is generated. Now we will define the parts as in which material belongs to which part. So first part is girder, material is girder. We select all these lines, and using control, so pressing control, we can then deselect the lines that are not representing the girder. So deselect all the edges here, and then you click apply. So that's the girder sections calculated. Now change the section type to slab, and this is part number 2, and the material is infill slab. Repeat the same process, select everything here and deselect just the lines over here, pressing control. So you have selected only the lines which should be the slab. And let me just change the color as well, so it's clear. When after calculation it will show you the color of the slab and the color of the girder separately, like this. So it has identified the slabs and the girder. Now I will calculate the properties. So calculate composite property. Mesh size for calculation of properties, 0.1 meters generally is a good enough mesh size. Now we select just any one part out of this. So it's best to select the base material, which is the girder, and click apply. Now the properties are calculated. Let's see what are the values for areas and moment of inertia. So composite property table, there you go. You have the girder, slab, and you have the girder plus slab. You can make a note of this area because this area will be used for applying the wet concrete load manually. So using this area, you can just convert it into a UDL and apply it directly on the precast girder when the slab is yet to be composite with the girder. Okay, so I'll close this, and now we will export this section into MIDAS Civil. So section, composite section, export, and we can select some name here, say TY8 composite, save, and click on the base material and click apply. So this section is now saved and ready for import into the analysis package. So similarly, we need to create such sections by importing on a new project. We go to new project and then import from AutoCAD the remaining sections, and similarly calculate the composite properties. So I'm not going to repeat the same process for the other girders. I've already generated the sections. So I'll go back to the software and go to properties, section properties, add, and go to composite, select composite general, and import the SEC files. So I import ty8, okay, and name this as ty8 infill. Okay, so we can recalculate the section properties. So if I say recalculate, we'll recalculate the section properties, and so that's the properties are recalculated, and I can click on center top just to make sure that this is the top is a reference line, and apply. Then tye 8, say left hand side, import, okay, and recalculate the section properties, center top, apply, and ty8 right side, import, click OK, recalculate the section properties, and then click OK to save this. Okay, so now I will create some groups for all these different girders. Groups are useful because later on when we try to display the results, we can just select a particular group to which will represent one girder, and look at the results for that girder only. So I'll go to group here, right click on structure group, go to the second new option here, and type in ty8 and suffix 1 to 12, and click add. Then similarly we have, so delete this, tye8 right, for example, and tye8 left, add, and close this. Now I will assign the groups, the elements to the correct groups. So using the selection tool, so that's my tye8 beams. This is ty8, say 1, ty8 2, ty8 3, ty8 4, ty8 5, ty8 6, ty8 7, 8 8, ty8 9, and ty8 10, 11, and then finally ty8 12. Then going to the second works tree, so you can bring in the second works tree by right clicking on this black bar, clicking on tree menu, works, and double click on ty8l and drag and drop ty8l, and also on the right one drag and drop the right group. Okay, so that's generated. Okay, now we'll apply the tendons, or automatically generate the tendon profiles for all these sections. Okay, now we will apply the tendon profiles. So we use the PSC bridge option and under the structure menu, tendon template, So what we first do is we add all the groups which have equal sections or the same sections. So we use this button here and double click on the different girders. So add, so just double click and keep adding. Add, sorry, 5, 6. Okay, so we have added 12 girders. Click OK. Right, now to see the section for each girder, we click on this the section, the element number, and we look, it will show us the total height and width of the section. Now we go to auto generation for the tendons, define a tendon property. So click add and enter the name of the tendon. So it's a pre-tension tendon, material is the high strength steel, total tendon area is selected, so strand diameter and number of strands, so we can choose from a variety of strand diameters. Click OK, and relaxation loss coefficient, European Eurocode, ordinary steel, and click OK. Close this and we click on OK again to generate the tendons. Now you will see that the tendon information is listed here. Now here we can choose to delete some of the tendons if we don't want all of them. So just select them and press delete, and we can also copy or move some of the tendons. So for example, I select these tendons, these 3 tendons here, and say move copy, and I can move them. So move in the DZ, Z direction is the vertical direction, so move by say 0.1 meters and click apply. So they will be moved up by 0.5 meters, 0.1 meters. So I'll bring them back again. I don't want to change the location, so minus 0.1, move and click apply. So before clicking apply, you can look at the position. The new position will be preview. You can look at the preview for the final position and click apply. Right, now some of the tendons may be debonded as well, so we can select the tendon to be debonded, say this one, and click on modify and enter the debonded length from the beginning and the end, say 2 meters from each end. So that's, this diagram shows what it will do. Okay, and maybe select another one here and say 2 meters and 2 meters. Click OK, and say one more here at the midpoint, modify, say 5 meters and 5 meters as a debonded length, and say another one here, modify 5 meters and 5 meters. Click OK, and now to assign them to all the sections, we can click on apply, and it will assign all the tendons to all these sections. If you are not able to see the tendon profile or tendon strand locations, you can go to display and check on, in the miscellaneous tab, you can check on tendon profile point to display the tendon points. From the top view, if I look, you will find that there are dots intermediate at intermediate locations on the girders. So these are the debonded strands. See, this is the 2 meter debonded strand, this is the 5 meter debonded strand points here. Now we will do the same thing for our TY edge beams. So what we do is just double click on the TY E or the edge beam group, say TY-E8R, and you see the previous tendon location is shown here. You can replace it by clicking on auto generate and click OK. That's the new profile. So again, similarly, we can choose to delete some of the tendons. Say delete this one, delete, and say delete the other one here. Say I want to delete few tendons over here as well, delete, and let's say I want to apply debonding to some of the tendons over here. So this one will be say 5 meters, click OK, and here modify say 2 meters, okay, and this one say 2 meters again. Okay, and you can click apply. Let's check. So that's applied here. Similarly, TY E8 L auto generate, click OK, and just like the previous one, delete some of the tendons, delete and delete here, and let's say delete some over here, and maybe debond some of them here. So 2 meters, 2 meters, and 2 meters over here, and finally 5 meters debonded. Okay, and then we click OK to save this. Right, so now we have applied tendons to all these precast beams. Now we will apply or change the section properties. So these are actually composite sections with slab on top. Now we will replace them with the infill sections which we imported from AutoCAD. So what we do is double click on say TY8 slab on top and drag and drop TY8 infill. Double click on TY8 left slab on top, drag and drop TY8L infill. That's this one over here, and right side drag and drop TY8 right side infill. That's it. All the sections are now replaced and you have got tendon profiles in all of them. So now what we can do is start modeling the remaining entities. Okay, just before this, we may also need to apply some cracked properties to the slab, especially near the abutments. So we'll have abutments here and here. So we can choose some distance from the abutment and assign it as cracked slab. So let's do that. So I'll change everything to line view and maybe undisplay all the tendon profiles. Now what I'll do is select these elements here and go to node element, divide elements. So I'll put in the distance from the start. So let's say we have 4 meters, or let's say 3 meters from the start, which we will assume as cracked, or we'll give it some partial stiffness. So apply. So that's just will give some lesser distance, let's say 2 meters. Apply, and similarly we can also do 2 meters from the other end. So this will be, if I select all the nodes here and go to nodes, translate nodes, and say copy in the X direction -2, and say intersect frame elements and apply. So just to see if it has properly intersected, I'll display the element numbers. You see there are 3 element numbers on each girder, which means it has the elements are now intersected. Okay, so to give them or assign them correct properties, you just need to go to properties, section properties, and generate some or copy the existing sections and give them some new names. So I'll copy this one, copy and modify, just rename it as cracked. Click OK, and copy this one as well, rename this one as cracked. Okay, and then this one finally copy and rename as cracked. Okay, now just select or select the sections like this. So these are all your TY8 cracked sections. Just select here as well, and drag and drop, and also TY8 left infill. So just to confirm which is the left, this is the left one, so left infill, and this one is the right infill cracked section, just to see if the shape's all correct. Yep, so that's all done now. Now we will define the abutments and piles and the remaining parts of the grillage model. Okay, so we will create the grillage model now. So what I'm going to do is go to structure, node element, and create elements. So my material will be transverse, and I haven't defined a transverse section yet, so I'll go and define the transverse section. Click on this box, add, and just give a name, transverse section, and say this is a solid rectangle, user defined. What I'm going to do is to make it a little conservative approach. I'll give, instead of taking the overall width, overall height of the thickness of the slab, which is approximately 900 millimeters, I will take only the top bit as the transverse element thickness. So just 0.15 meters, 150 millimeters, and I'll divide the grillage into 1 meter segments. So the width of the transverse member will be 1 meter, and I'll change this to center top so that it is well aligned with the top of the deck, and I'll click OK and close this, and just change the section to transverse. Just draw it over here like this. Now select recent entities, and I'll copy them, translate. So I'll measure the distance, say like this, or what I'll do is yep, so measure the distance, and let's say divide it by 15, say 15 times. Okay, and intersect node element, and click apply. So that's it, it's divided now. Close this. So the grillage model is complete. Now we will assign the abutments and piles. So to create the abutment, first of all I will create the bounding area of the abutment, the lines, the outlines of the abutment. So just selecting the cornermost points like this, and we'll create lines out of them. So create elements, extrude elements, and say, let's say concrete for instance, and what I'll do is used some dummy sections, because these lines that I'm going to draw are just used for modeling purpose. I will not need them for analysis, so I'll just assign a very small stiffness, 1 millimeter by 1 millimeter. That's dummy, and say Z direction, so minus, say the abutment is 2 meters deep, so -2, and apply. You can check from this view, that's the abutment been drawn. Now I'll join the two lines, so join the lines like this, and another one here like this. Just undo it, I didn't select the correct property. That's concrete, and say dummy, okay. Now just changing to the side view, I'll create the pile locations. So we have got, if I go back to the presentation or the image here, we have got 6 piles. Okay, so approximately we'll take the distance as 1 meter from either edge for the end piles, and then divide them equally, and the remaining portion will divide them equally. So selecting this node, the nodes on both the abutments, we'll right click, go to nodes, translate, and this is the Y direction. So just going to the top, so Y direction, let's say Y -1, and intersect elements, apply. Then do the same thing on the other side, this time Y +1, apply. And now whatever is the element here, we'll just divide it into 5 equal parts. So divide elements and 5 parts, that's done. Now using these parts here, so I'll change it to the side view. So select all these new nodes, so there are 6 nodes on each abutment, and we will extrude them. So extrude. Okay, so the material is concrete, section will be the pile section, so I'll add another section here, solid round, that's the concrete pile. So pile, user defined, say this is 750 millimeter dia pile, close. And the pile, the total length of the pile is say 10 meters, so -1, 10 times, and click apply. So the piles are now generated. Just to make sure I have defined the sections correctly for the piles, I'll just drag and drop the piles section again. Let's see. That's how it looks. Now we will mesh the area here to create the abutments. So abutments will be modeled as shell elements. So changing back to the line view, so I'll go to node element, auto mesh option, and select nodes, and say quadrilateral elements. Select the thickness box and define a thickness. Abutment is 1 meter wide, 1 meter thick. So click OK, and we will mesh the area. Just select the nodes and give some. So that's say 1 meter, and apply. that's the abutment generated. We can refine the mesh slightly, so make it 0.765, apply. That's a more finer mesh, but usually 1 meter is sufficient, because 1 meter forces that you will get will be the per unit width of the slab, so that will be the design forces directly. So let me just change it back to 1 meter again and click apply. Same thing will do for the other side abutment, so just create the abutment like this and click apply. Okay, let's check the how the fleshed view looks like. So that's how it looks. Now if you are not able to see the thickness of the slab, or sorry, the abutment, then you need to check on the option. So display option, draw, check on the hidden option, frame thickness and plane thickness, and you will be able to see the abutment thickness. So that's the model generated. Now we will apply some loads and boundaries to the structure and model the construction stages. So to create the construction stages, we need to group the remaining elements as well. So group, we'll select, we'll make sure that all the elements are correctly assigned. So let's say the abutments, all the thickness, 1 meter thickness elements, they should be concrete material. Then we don't need the dummy element here, so we'll just double click on dummy, click on the screen and press delete to delete them. Okay, and we will make sure that precast girders are all precast girder elements. Concrete slab is yet to be assigned. Transverse elements are defined as transverse materials, and here as well. Okay, now we'll create another structure group, new, and define this as a substructure. The substructure, and make sure that the substructure is everywhere the substructure is assigned as the abutment and piles. So I'll highlight all the abutments and the piles like this and drag and drop substructure. We also need to create boundary groups. So first I'll define the boundaries. So it's an integral bridge, so we'll define the soil stiffnesses, spring stiffnesses around the piles. So we'll go to boundary, integral bridge, pile spring, and say first 5 meters are clay soil, so say soft clay. Ground level is top of the pile. The pile diameter is 0.75 meters. Coefficient of subgrade reaction, which can be obtained from the SPT test, say 10,000, and apply. And similarly we can do the remaining parts. Say this is sand, or it can be bedrock as well. So if it's bedrock, we'll define some higher value of coefficient of subgrade reaction. Click apply to define the stiffnesses. And now we will define the boundary group for all these piles. So group, boundary group, new, soil springs, and just select on the piles here. So basically all the abutment and piles, whichever node is applied with the boundary, they will be considered in the soil springs boundary group. Click OK. Okay, so that's done, and now we create some load groups as well. So new, so this is self weight of the precast girder and other concrete elements. Then we have wet concrete, that's for the slab, infill slab. Then we have earth pressure, which is calculated from the PD document. The K star values are calculated for passive pressure and applied on both the abutments at the same time. Then some other loads like surfacing can also be applied. Let's go with these loads and then we will apply some more. Okay, so we go to loads, static load cases, and give some names, load case names. So that's self weight, enter say dead load, add wet concrete, add, and say earth pressure, add, say surfacing, add here. Okay, now I will activate only the deck to apply loads on the deck, only on the deck. So select all the deck elements and press the activate button or press F2. Right, so now I'll start with applying self weight. Select the load case name, group name, self weight, Z -1 in the gravity direction, add, self weight is applied. Then we apply wet concrete load. So elements, say wet concrete load here, and select all the precast girders. So group, and just press shift and select all the precast girders, right click and select. These are all the precast girders, and let's say TY8 beams have a particular value of wet concrete. Select, say all these TY8 beams have -10 kilonewtons per meter as the wet concrete load. Apply, and let's say TY8R and L, select. They have some other values, say -8, -7 for instance, -7, and apply, and close this. Okay, then we'll apply some surfacing loads as well. So surfacing loads can be applied directly on the precast girder, or they can be applied as a floor beam load in a two-way distribution manner. We can apply the surfacing loads, but let's assume that it's applied directly on the main girders as a UDL. Element beam loads, surfacing, and this time I'll select all the TY8 beams, assuming that all the carriageway the surfacing is entirely on the TY8 beams. Select and -10 again, and apply. That's done. Okay, I'm not applying any H-beam load or parapet beam loads just to save some time. You can apply similar loads and other dead loads, like construction loads, wherever required, in the same manner as a UDL can be applied to all these elements. Then earth pressure loads. So activate everything and just activate the plate elements. So active. Select all the plate elements, then hydrostatic pressure, earth pressure here, and reference height is the top of the abutment. Constant intensity or horizontal surcharge, say it's -5. Gradient intensity, this should be gamma times K star, or unit weight of soil times the K star value calculated from Eurocode 7. Say -20, and apply. So it's been applied in this way. Now it's actually the opposite direction, the way it has been applied. So we can either change the sign, undo and change the sign, or we can change the local axis itself. So just let me undo and change the sign, and again apply. There we go. So that's correct now. Okay, now we will define the construction stages. So the first construction stage will have only the abutment and piles with the earth pressure load. The second construction stage will have all the precast beams placed on the abutment, so they can be modeled, and then we will have all the concrete poured and also the precast edge beams placed on top of the existing the TY beams. So let's see how to do that. Now for the for construction of or placing, when we place the precast beams, we assume that they are simply supported, and then when we cast the deck, the entire thing becomes composite, including the integral abutments and everything. So let's give some moment releases to our precast girders, the TY beams. So I'll go to groups and just define a new boundary group. Say this is a moment release, and what we will do is activate all the TY beams, select all of them and say active. So all these beams, go to the top view, boundary, beam end release, and say we select all these elements here and define them as pinned fixed. So these are all pinned fixed. Apply. So these ends are all pinned. You can see that the symbols. Then this end is fixed pinned, and apply, close, and just make sure that these are all assigned in the one boundary group. So I'll just select all these elements and drag and drop moment release. The beam and release will be assigned. Click OK. That's done. Right, now we will go to loads, construction stage, define CS, add, and say stage 1. Duration of stage 1 is, for example, just keep it as 10 days, for example. Say 10 days, and all the substructure elements should be activated here. So all the piles and abutments should be activated with full strength. So 28 days age, add. All the TY beams and all other the TY edge beams should be activated in stage 2. So boundary, soil springs, so add soil springs. Loads, self weight will start acting from the very first day, and also earth pressure loads will be start acting on the first day itself, and apply. Then we go to stage 2. We start with all the precast beams should be activated with an age of 28 days. So when they have attained the full strength, they will be activated. Or we can make it slightly conservative by taking in 7 days, for example, and applying the pre-tension also on the 7th day. Or if we don't want that, we can just put in 28 days, add, and go to boundary, add this with the moment release. So add with moment release. Loads acting on the precast girder will be wet concrete load from the very first day. Now this duration is 7 days. Why I'm keeping it as 7 days? Because after just after 7 days of this construction stage, the concrete will become composite. So when we activate the deck, it should have an age of 7 days, and that should be entered correctly in the composite section definition. So now I click on apply. Then we go to stage 3. Say this is the stage with 1000 days, for example, for long-term effects. Now in this stage, we haven't generated any transverse element group or any or the edge beams group, so we'll go and generated them. So structure group, first the transverse group, activate everything, select all the transverse elements, drag and drop, and similarly this is edge beams, so the parapet beams, the edge beams which support the parapet. Okay, now we go back to define construction stage, add, and add stage number 3, and just give it a long duration and activate the transverse beams. Age is not important here for transverse beams because we are not going to consider creep shrinkage properties for transverse. Also for edge beams we are not going to consider any creep or shrinkage property, so add them. Then boundary, or to be safe you can actually make it 28, so in case you mistakenly assign any age, any creep and shrinkage property, you will have the full strength considered for concrete. Now boundaries, now once the slab is becomes composite, then we will deactivate the moment releases, so deactivate them so that they will be again they become fully integral. And loads, we activate surfacing, but we activate surfacing on the 21st day, that is when the slab gains its full strength. So we add another day here, 21, select 21 from here, and surfacing, add it in the activation menu and click OK. So all the stages are now added. Now we need to make sure that we have got all the composite sections parts separated out. So we go to composite section for construction stage, add, and we start defining some composite sections. So start with TY8 infill. So this section is activated in stage 2, and material is precast girder. Stage 2, age of activation is 28 days. Material, and we have slab material, and this is in stage 3. The slab will come in stage 3, and the age will be 7 days age, and we click apply. Then similarly stage TY8 left, precast girder, stage 2, age should be 28 days. Material, slab, stage 3, and that should be 7 days, apply. Then we change the section to TY8R, material, precast girder, stage 2, age should be 28, material, slab, stage 3 with an age of 7 days, apply. And now we move on to the cracked sections. So cracked, material, precast girder, stage 2, 28 days, material, slab, stage 3, 7 days. Now for each part we have got stiffnesses mentioned here. So for slab we have got these stiffnesses. We need to edit them so that we can consider the cracked properties correctly. So we go to stiffness scale factor, and we can keep all the stiffnesses, we can change them to 0. So weight is 0, area 0, so that is assuming that we have full or 0 stiffness for the slab. So we are assuming fully cracked. If it is partially cracked, we need to enter some stiffness scale factors here. So click OK and click apply. Then we go to TY8 left infill, materials, precast girder, stage 2, age is 28, slab, stage 3, age is 7 days, we change all the stiffness scale factor to 0. Then finally the right side infill crack, precast girder, stage 2 D8, slab stage 3 7, click OK and click OK to save all the sections. Now let's see how the construction progresses. So we'll change to the fleshed view, look at stage by stage. So first stage, we have got only abutment and piles. We have got earth pressure, self weight, all the springs are there. Stage 2, we've got all our tendon profiles, the beams are all in there. What we haven't yet applied in our construction stages is the pre-stressing. So the pre-stressing needs to be applied. So let me just go back to base stage, create a group for pre-stressing. That's pre-tension, for example, and we create another load case for pre-tension. So load static loads cases and pre-stress, for example, that's the name. That's pre-stress, add. And now we go to temperature pre-stress, tendon pre-stress, select pre-stress and the group pre-tension, select all the tendons. So press shift and select all of them, bring them to the right hand side, and we assign them with some stress, jacking stress. So Newton millimeters, I'll change the units to Newton millimeters, stressed from both ends. And what I'll do is, since we are activating on the age of at the age of 28 days, so we will apply the jacking force as not the actual jacking force. Let's apply it with some reduced jacking force, because we haven't considered the early shortening of or early shrinkage of concrete or creep in concrete, which may lead to further losses, because we are activating all the precast girders at an age of 28 days. So I'll just apply a reduced value of jacking force, say 1000 MPa, and click add. That's added. Close this, and you can display the pre-stress forces, display, and so I'm displaying. So construction stage, define construction stage. These will be activated in stage 2. So modify, loads, pre-tension from the very first day, add, and click OK and close this dialog box. Let's look at the stages again. Stage 2. So we have got pre-stress in stage 2, earth pressure, wet concrete and self weight. And in stage 3, and also we have got releases. If you see here, beam and releases are here. Stage 3, there are no releases, all the transverse members are there and all the composite section is there. Going back to the base stage, now I will make sure the moving loads are applied. So again, activating the deck, changing back to the line view, and I'll activate the deck. Just make sure edge beams are in. Yep. Right. So for the deck, for applying moving loads, we'll go to moving load option, select Euro code, say traffic line lanes, add. So we will define 4 lanes, 2 footway lanes and 2 notional lanes. So footway 1, eccentricity, we'll measure all the lanes from this line here, bottom line. So eccentricity is minus 2 meters, 2000 millimeters. Let me change the units to meters here so it's easier to apply, and kilonewton. So minus 2 meters, 3 meter is the width of the footway, first footway, and the distribution type is via cross beams. So I'll select the group consisting of all the cross beams, which is transverse group, and draw the lane like this and click apply. So that's the first footway lane applied. Then we have got notional lane 1. So we don't know whether it is notional lane 1 or 2, so I'll just name it lane A to avoid confusion. Okay, so for the notional lane A, I'll remove the previous data, so delete the previous data, and eccentricity I'll enter as roughly 4.83. Wheel spacing is 2 meters and the lane width is 2.75, and the same way generate and click apply. So that's lane A generated. Then we generate lane B. Okay, so 7.58. delete the previous information and create the lanes again, apply, and then finally footway 2. So delete the previous information. This one I will measure from the top element there. So the eccentricity that I will enter is 1.5 meters, and wheel spacing 2, lane width is also 2 meters, and just draw the line like this and click OK. That's footway 2 entered. I'll close this and move to the model. Okay, now I'll go to vehicles, add standard, load model 1. So as per the UK National Annex, we'll enter some adjustment factor for load model 1, 2.2, and the psi factor as per UK National Annex, apply, and then load model 3 UK National Annex vehicle, say SV196, and say user input, or say just put in SV100 for now. Let's say user input for dynamic amplification factor 1, 2, apply, and footway and footbridge loads, so 5 kilonewton per meter square. So let's say reduced value should be used for group 1A combinations, so 3 kilonewton per meter square with a psi factor of 0.75, and this is, I'll just type in 0.6 times footway, apply, and just say the normal characteristic value footway, which will be 5. So I click OK. If there is any type of other types of vehicle, you can define it from add user defined vehicle. So user defined load model 3 and load model 1 can be defined. So I close this and go to moving load cases, add, and type in the load case names. So group 1A, which is load model 1 and footway, so we ignore psi factor, consider only characteristic value. 0.6 times footway will be used, and define all the lanes, bring them under footway lanes category, and apply. Then group 5, which is load model 1 and 3. For this we will consider psi factors, load model 3, and consider these two lanes as the straddling lanes. So load model 3 will straddle between lane A and lane B, and click OK. So these are the two main load groups of combinations. So I'll activate everything now. Sure. Okay, so we are interested in looking at the results of the elements for live load analysis and for construction stage analysis. So just to make sure that we are considering creep and shrinkage effect in the construction stages, I'll just define creep and shrinkage properties. Go to creep and shrinkage, add, and define first for precast beams. So precast European standard, and we just enter 40,000 kPa, which is the strength of concrete. And notational size, we can put in any value of notational size, say 1 meter, because the software automatically calculates in the construction stage what is the notational size. Show result, and that's the result for creep and shrinkage. Apply, put in another one for slab. This one is reduced strength 30,000, and click OK. Then we put in similar things for compressive strength gain. Add, name is say precast European code, and this should be mean compressive strength, so FCK plus 8 or 48,000. Click OK. Add again, this time for slab Eurocode 38,000. Redraw, click OK. Close this, and now we will link the materials with the functions with the correct materials. So precast with the precast material, add, and slab with the slab material, add, and close this. So now we can run the analysis and see the result. To run the analysis, we use the analysis button, perform analysis. So analysis is done, and now we can look at the results. So let's say results, we can generate some combinations here. Go to load combinations, type in some names, say for example ULS, and select all the cases. So dead load effects from construction stages, define it with some factors, say 1.35, and effects from pre-stress, tendon primary 1.35 again, let's say secondary effects as well 1.35, creep and shrinkage effects, say creep secondary 1.35, and also shrinkage secondary, which is factor 1 for example, and load models, so group 1A, say with a factor of 1.5, and so on. So we can create similarly many such combinations. So I close this, and we can look at the deformations, displacements, say stage 1, and let's say deform legend, make sure millimeters is on, and I'll just close this tree menu, we don't need it now. So we can look at the deformations due to different effects, dead loads or pre-stress or creep shrinkage. Click apply. That's the deformations due to earth pressure loads. We can clear up the legend by making it fixed format. That's the deformation stage 2. Stage 2, see you have 93 millimeters deformation. Stage 3, we've got some more deformations here. And then stage 4, stage 3, this is including your creep and shrinkage results, so 98 millimeters is the final deformations. Then we can look at the forces, so beam diagrams, say stage 1, let's see, we'll check off the deformed shape, solid fill, make sure it's kilonewton meters, and click apply. That's the bending moment diagram in the piles. Stage 2, we have got summation, which is including dead load and pre-stress. So these results that you're seeing are summation. If you look at the dead load results, you'll get the more expected type of graph like this. So you see this is the beam end releases were used, so you have zero moments at the ends. Then if I go to tendon primary, that's the primary pre-stress effects, and if I see summation, it will show me the total bending moment in the pre-stress girders, precast girders, and you see all are in the red zone, which means they are positive or sagging bending moment. Then we'll move on to stage 3. So stage 3 gives us the bending moment in both steel and precast girder and slab. If you want to see in slabs and girders separately, change to part 1, which is girders only. Apply. That's the bending moment in the girders, 1300 kilonewton meters. Then part 2, which is slab, click apply. So that's the bending moment in the slab. If you see, there is zero bending moment at 2 meters from either end of the abutment, because the slab we have considered as cracked, so there is no bending moment in the slab. Similarly, we can look at stresses to check if the pre-stressing, the stresses, combined stresses due to dead load and pre-stress are in the allowable limits or not, or whether there is any tension. Those things can be checked. So combined stress and say bottom flange, bottom of the girders, so make sure it's part 1. Apply and say solid fill, apply. That's the stress distribution. Minus indicates compression. And if I go to part 2 and look at the top flange stresses or top fiber stresses of slab, so select point 1 from this figure, apply, and that's the distribution of the stresses in the top of the slab. So you have the blue indicates compression, and somewhere here you have a little bit of tension at the ends. Okay, so I close this, and all the results you can look at in a tabular format from result table, so whichever results you want. Now we move on to moving load tracer, moving load results, live load results. So you go to results, forces, beam diagrams, and look at say group 5 results. MV max and min. Max and min give you the positive and negative force effects. So generally positive moment is sagging, negative moments is hogging, and yeah, and negative force is compression, positive force is tension, axial force is tension. So MY selected, legend, apply. Just click on solid fill. Let's look at the result here. So you're getting a maximum sagging bending moment as 470 kilonewton meter, and that's in element number 297. So we can investigate the position of the vehicle causing the worst bending moment. We can go to moving load tracer, beam forces moments, and type in the element number, say 297 for moment, and click apply. This shows us the maximum, the vehicle position causing the worst bending moment. So if I see from the top, see that's the vehicle position, and you can clearly see the straddling effect here. That's load model 1 axle, and the load model 3 axles have straddled in the transverse direction between lane A and lane B, and that's how this shows the arrangement of the vehicles causing the worst bending moment at the midspan. Then we can look at the loss graphs for the tendons. So if I go to tendon loss, say stage 2, that's the variation of the tendon force, and stage 3, so stage 2 tendon force, there's very little tendon force that we applied initially. So to start with, the tendon force was very less applied, and also the tendon area was may have been very smaller, so we have very little pre-stress force in the tendons. But as we go through different strands, we have higher tendon force in some of the strands. Okay, that's the force variation in different tendons. Okay, and so that gives the basic picture of what type of results you can obtain and how to model the composite precast girder bridge with an infill type of deck. So that's it. For more types of bridges, stay tuned to our YouTube channel, MIDAS UK. Thank you very much.